We will go ahead and get started. Go ahead and get your refreshments. There's no hurry. Uh, and do whatever you got to do, but we got a lot to get through today, so we're going to get started as soon as we can. So my name is Jeff Carr. I don't always introduce myself, but we have a lot of new faces today, and it's fun to see you here. So I am the Senior Director for External Affairs here at the Museum of Idaho, and one of my duties that I enjoy is that I get to oversee this wonderful museum club lecture and presentation series. So for those of you who are new around here, how this works, during the summer, we do just once a month, but as soon as September starts, we'll be going back to twice a month, every first and third Thursday here at 3 o'clock. Wonderful expert presenters on a variety of subjects through the humanities, sciences, current affairs, and it's a lot of fun. So we'll welcome you all back anytime. So a couple of other housekeeping notes while I'm here. Please, if you haven't already, silence your phones for the duration of the presentation. If you need to step out, you can step out. That's fine. Let's see, our next museum club presentation. So we're still on the once a month summer schedule. So August 18th, Thursday, August 18th, we will be discussing the USS Idaho, a submarine that has had a wonderful wartime naval history and is being recommissioned, or rather a new one under that name is being commissioned for future use. We're going to talk a little bit about that submarine, the USS Idaho, on August 18th. Also keep in mind that we are about a month out from our annual fundraiser gala, or gala if you prefer. We sort of go back and forth. Both are okay. It's going to be Friday, August 26th here in the museum, a lovely formal event, and we hope to see you all here raising money for our wonderful nonprofit here, our 501c3 nonprofit Museum of Idaho. Everything we do relies on the goodwill of the community. So let's get into this presentation a little bit. So first of all, just say we are going to be taking questions at the end of this presentation rather than during. We have a lot to get through. We want to make sure we get through as much as we can. And so if you do have a question, you are welcome to write it down. We've got note cards and pens. If you need one, they're right there in the back if you don't have one already. Write it down so you don't forget it. And if you're on Zoom, you're welcome to put your question in the chat as well, and we will get to it there at the end. So let's see what else. I guess I should also note that our presenter has brought a number of fantastic visual aids today for you all to look at, and there will be plenty of time after the presentation and the Q&A to be able to step up, and he's kindly agreed to stick around and explain some of what we have here. There's really a lot going on, so welcome to come up if you need to. If you have to leave when it's over, there's no problem. You're good to go there. So without further ado, it's my pleasure to introduce Bill Thielbahr. Bill Thielbahr was born in 1939 and raised in Sacramento. He has earned a PhD in mechanical engineering from Stanford University, go Card, in 1970. Sorry. He has been married since 1961 and has 2 daughters, both graduates of Skyline High School. He began his professional career in 1961, working for the Department of Defense at the Naval Weapons Center in China Lake, California, transferred to the Department of Energy in Idaho Falls here in 1979, and then retired from federal service in 1995. Bill's lifelong interest in rocks and everything associated with them began back at China Lake in the early 1970s. He bought his daughter a small rock tumbler, and from that time, he couldn't stop exploring all aspects of rock collecting, cutting, polishing, and displaying them in various settings. After retirement, his hobby intensified, and in a few years after taking a class in faceting gemstones in Quartzsite, Arizona in 2000, he decided to enroll at the Graduate Gemologist program at the Gemological Institute of America in Carlsbad, California. He received his graduate gemologist diploma from GIA in November 2003. and he has provided independent gemological services ever since, which essentially means he doesn't work for anybody. He doesn't work for a jewelry store. He is here representing himself. Now, Bill has been a member of the Idaho Falls Gem and Mineral Society since he first arrived in Idaho Falls in 1979. He assists the society by giving lectures on various aspects of rock and gem identification, and assists the society in their sponsorship of two major gem and mineral events each year here in Idaho Falls: the Gem and Mineral Show in April and the Members Sale in October. He's also been a member of the Quartzsite Gem and Mineral Club for many years and has given several lectures on various aspects of gem identification, and I have been trying to get him to speak here at the museum for quite some time. So I'm really excited to have him here. And without further ado, Bill Thielbahr with How a Gemologist Identifies Gems.
Okay, in the pocket. All right, thanks, Jeff, and welcome. I hope you're here, all of you, to learn how a gemologist identifies gemstones. If you're not, stick around. You're going to find some interesting stuff. Now, gemology is a complicated field. It might surprise you. It's made complicated because it involves several different areas of science. A gemologist does not have to have a college degree, but I can tell you, as an old PhD engineer, it's challenging, especially when you peel away the layers. And if you're curious, trying to find out why things happen, it's complicated. So we fill this hour with lots of stuff. And as Jeff said, please hold the questions in the interest of time until afterwards. So we have, what are these areas of science I talk about? I've showed here, certainly geology and the chemistry of gemstone formation. That's a big area of science. And we're not going to talk about that today. We don't have time. The physics of light and color, we will talk about. And we will touch on some solid state physics having to do with the molecular and atomic structure of gemstones, which is important. The design of instruments that measure the gem's response to all kinds of electromagnetic radiation, which we'll talk about in a moment, that's a big area of science. These instruments are very sophisticated, very expensive, but they yield a lot of useful information. And synthetic gems scares the bejeebies out of me because they're so hard to detect. But there's big science chunks in coming up with new ways to synthesize gemstones. Diamonds, of course, are a big topic today. Next. So what is a gemstone? Well, people like it. It's colorful. It's got patterns that are exciting. It's safe to use. You can cut and polish it. We all know that gemstones have to include diamonds and colored stones. That goes without saying. But it also includes pearls and shells. What is not a gemstone? And I get too many of these. Are specimens people pick up at mine sites, and they're all glittery with zinc and lead and silver crystals. And they come to me and they say, what is it? That's not a gemstone. Next. Color dominates the buying, selling, and grading of gemstones. It's king. So we're going to talk a lot about color. Color depends on light. Okay, what is light? Light is a narrow region on this electromagnetic spectrum that I've shown here. I know you can't all see it, but the electromagnetic spectrum is full of things, words that you've heard: gamma rays, X-rays, UV rays, radar waves, infrared waves. These are all forms of electromagnetic radiation that have certain things in common. They all travel through space at the speed of light. They all have, which is 186,000 miles a second, in case you're wondering. They all travel in wave-like forms. Consider this to be a wave. These particular forms of electromagnetic radiation have a wavelength measured from the beginning of the wave to where it's repeated. The waves also have a frequency. How many waves pass a particular point in time? Cycles per second. A cycle is one of these. So we talk about electromagnetic radiation in terms of its frequencies and its wavelengths. These waves are traveling, boom, real fast in a straight line at the speed of light, but it isn't just like this. Sometimes they're moving like this, this, and this, and this, and we'll get to the importance of that later on. So we have the spectrum of electromagnetic radiation. We're going to start from the left-hand side, high frequencies, low wavelengths. They go hand in hand. High frequencies, lots of energy, small wavelength. We're going to start with gamma rays on this end. Gammas have a wavelength of 0.01 nanometers. So you say, who cares? Well, we're going to talk a lot about nanometers. A billionth of a meter is a nanometer. As we progress to the right on this spectrum, we hit X-rays. What is their wavelength? 1 nanometer. We're getting bigger now, larger wavelengths and smaller frequency. Then we hit UV, ultraviolet, at 100 nanometers. Then we go a little bit further, and right here, right there is our light spectrum. It starts at 400 nanometers and it ends at 700. That's the world we live in. That's our colors. That's everything to us, 400 to 700 nanometers. So this is called the visible spectrum. It's right here, so tiny I can barely fit it on this spectrum. If we go, if our eyes are radiated by this particular form at 400 nanometers, our brain tells us, our eyes receive that radiation, sends electronic signals to the brain comes back and says violet. 400 nanometers, we see violet. At 700 nanometers, we see red. And all the colors in the rainbow in between 400 and 700. So beyond 700, beyond red, we enter a region called infrared. That's where that term comes from, far red, beyond 700. Infrared extends out to about 10,000 nanometers. As we go out further, we don't measure these radiation forms in nanometers. We measure them in feet, hundreds of feet. We don't care about that today. We're talking about light spectrum, which is 400 to 700 nanometers. So it turns out that if you have a light ray, if you have light rays, they're all full of these colors from 400 to 700. If you mix all the colors from 400 to 700 nanometers in equal amounts, you end up with a white light. I don't mean white like that white. I mean, there is no color. You mix all those colors at the same amounts, you'll end up with this thing called white light, which we won't pay any attention to from here on, but I just want to point that out. For a very long time, certainly my lifetime, through today, the gemologist identifies gemstones using just light. You don't need all these other forms of electromagnetic radiation. All of what you hear today is a product of light. Now, unfortunately or fortunately, depending upon if you're in or out of the research community, for the last 20 years, there's been an explosion in the development of instruments and analytical techniques that examine gemstones at using other forms of electromagnetic radiation. Yep, Virginia, back that up. UV, X-rays, which is beyond, and infrared. So there is a ton of information on how a gemstone reacts to those forms of radiation. Those are outside light spectrum. So how does that help a gemologist? Well, it helps in a couple of ways, and we'll talk about that. Those instruments are outside the financial reach of a gemologist. They're very expensive, and only gemologists that work in laboratories and universities and large companies that can afford them, they're the only ones that can generate this information. But there's so much available in the open literature, that's not a big impediment to a gemologist. So keep in mind that these advanced techniques, Virginia, they have given us information about these secret gem treatments. They're always secret when they come out. They drive everybody crazy, and the research crowd comes out of the woodwork trying to understand why it's changing the gem color. And since color is king, you better know why, because a gemologist is going to have to deal with that if somebody comes to him or her with a stone that's been treated in some way. So understanding treatments has been one of the products of examining gems outside of light spectrum. Fortunately, the information that's out there and that's being generated as we speak beyond light has not affected this proven process, which you'll hear today, as to how gemologists identify gemstones. I will use light. It will be, the gemologist will use light for the next 20 years, 50 years, maybe. But there's going to come a time when all of this new information that's been generated is going to affect this proven process. It could come a time when there is an instrument, you have an unknown gemstone, you have an instrument, you zap it, and it tells you right away what it is. It's going to put all the gemologists out of business. It's possible the way information is being generated, but not today. If a gemologist cannot identify a gemstone using the proven process, which in the first time I've been stumped, then we are forced to go to these research labs using these advanced instruments, hopefully to answer the questions. Next. This is the simplest possible concept I can think of to explain color. We have these light rays. Remember, each of these red light rays has all these colors mixed in with it. It impacts a solid material. It could be a gemstone, could be this wall, and the material that it impacts absorbs certain wavelengths. The rest is reflected back to our eyes. So when our eyes look at this surface, our brains and all these cones and rods in the back of our retina tell us what the color of this is from this reflected light. It's these wavelengths minus what's absorbed is what bounces back. Now, I show this for opaque materials. That means you can't get light through it. This simple concept also applies to transparent materials, which are popular in the gemstone, in the gem world, in which case these rays will pass into the transparent material. Some of the wavelengths are absorbed and they'll bounce around, and we'll get into the internal reflection next. So we've talked about the causes in a very simple-minded way. To review, the cause of color is how our brain and eyes process the wavelengths that hit it. The properties of the light source is important, which we'll talk about, as well as the physical and chemical properties of the gemstone. Next. So what are the light sources? Well, we have the sun, we got incandescent lights, we got fluorescent lights, we got LEDs. We're going to call the sun daylight. What are the properties of these sources of radiation, sources of light? Remember, we're in this spectrum, this light spectrum. If we had a spectrophotometer, it measures the intensity of photons, which are these bundles of energy that are traveling through space in a wave-like form. This instrument will measure the intensity of the photons at their various wavelengths. And this is the spectrum then of daylight. A place on Earth, a place in time, you measure the daylight spectrum. You see it has a preponderance of emissions in the blue range, in the 500 nanometer range, with less in the violet and less in the red. Next. This is the incandescent spectrum. You know what incandescent lights are? I grew up with those. You don't find many anymore. They're all LEDs. This is incandescent. This is the spectrum of an incandescent. So you see it's heavy on the reds and not so heavy on the blues and the violets. Now, let's talk about the importance of this. If you're selling a blue sapphire for a lot of money, and you've got a customer sitting there at your table, you want to show those blue sapphires under daylight because it's got a preponderance of blue. That's the way business is done. If you have rubies and you're selling your customer rubies, you want that light source to be an incandescent. Heavy favors the reds. That happens all the time. So the importance of the light source cannot be overstated. Next. This is the spectrum of a fluorescent bulb. Here we have 3 phosphorus coatings over our fluorescent bulb. You can put more, but if you know what the phosphorus coatings are, you can get a spectrum with these spikes at various wavelengths. And if you're careful about the phosphorus coatings, you can actually get something that mimics daylight. The light that I have here is a daylight equivalent fluorescent light. And you'll see when I later on what it looks like. But that's what I examine my gemstones under. It mimics daylight. Next. LEDs, the new kid on the block, that's its spectrum. We won't go say any more about LEDs. So we've talked about our eyes, we've talked about the light source. Let's talk about the properties of the gem. Super important. The surface properties. The surface properties have a lot to do with what we see. If the surface is rough, then the light that hits the surface will scatter and it will affect what comes back to our eyes and therefore the color. If there's a nice polished surface, smooth and polished, like gemstones usually are, that will give us a true color. If you could groove the surface of a gemstone, you can get some fantastic colors. Now, who's going to groove a surface? Believe me, folks in the diamond world have tried this. This is a CD, and the grooves of this CD, guess what their dimensions are? Between 400 and 700 nanometers. When you get light reflecting off of these grooved surfaces, you can get a super spectrum of colors. So the surface properties are important. The chemistry of the material is everything because you're absorbing wavelengths, and that absorption phenomena requires a certain chemistry and not only the basic chemistry of the gemstone, but any trace elements that might be there. That's where solid state physics comes in, is understanding what the makeup of that gemstone and how light causes color. Then you have this thing called reflection. It isn't the reflection I showed you in that simple-minded chart. This is the reflection you get from a transparent material. Remember, I told you that the other chart or the graph was opaque. These rays that are incident will enter that transparent material. They'll bounce around, and if you design that gem right, if you cut it just right, those light rays will come back out the top of that gem and look you straight in the eye. That's color. So that internal reflection, I say external here because it emerges, and we'll talk about what conditions will it come out later on. Next. So how do you describe color? You describe it by its hue, its tone, and its saturation. Hue is the basic body color. Tone is the lightness, no color. So it's just the lightness or darkness. And saturation is the intensity of that color. Is it washed out or is it vivid? GIA has pioneered in this method of describing color. GIA, remember I went through the GIA school, so I'm tainted, has, and this is used everywhere, has a color wheel. 31 hues is all I was taught in 03 when I went through their school. 31 hues, and it tells you what they are. This is what we select from. There's been a new process that's come out, a new color grading process that's come out. Gemworld is the sponsor. They have now 100 hues. The tones, what does GIA tell us about the tone? Here's what they tell us. There it is. This is light and this is dark, and there's 8 levels, and you choose the tone. Same with the saturation. They show us examples here of what saturation is for 6 levels. And I'll tell you, if you're trying to identify a gemstone, you better know its hue, tone, and color. That's if you're going to grade it. And you have to pick a tone, and you have to pick a saturation. That's not easy. That's subjective. Gemworld has 10 tones, just like GIA, but they've increased the saturation to 16 levels. The importance of that will come later. Next. I can't overstate the importance of color. If you have the right hue, tone, and color, as tough as tone and saturation might be, but if you make your best guess and you happen to hit the right hue, tone, and color for an emerald, then you can call that green stone an emerald. If you don't hit that green stone with the right hue, tone, and saturation, you can't call it an emerald. You have to call it a green beryl. Beryl is the family where emeralds live. It has to be the right color. And of course, if you got the right color, it's worth a lot of money. Same with rubies. If you have a piece of topaz, colored topaz, peach-like, if the hue, tone, and saturation is right, you have imperial topaz, and the price just shoots through the roof. Paraiba tourmaline, Padparaja, sapphires, all depends on the hue, tone, and saturation. Next. Now we're going to get into the physics of light. Now I know the kids are going to pass out, but nonetheless, they might learn something. So we have a light ray, remember it's full of colors, hitting a solid surface. It's traveling through air at the speed of light. When it hits this surface, there is a reflection, but we don't care about that right now. It slows down when it hits a solid, higher density material. It slows down and it bends. So this ray is refracting. The amount of bending is called refraction. And the refractive index, the RI, is calculated, is defined as the speed of light in the air, which we know, over the speed of the solid, speed of the ray in the solid, which you just don't go out and pick up an instrument measure. There are ways to do that, however. So all materials have an RI. Gases have an RI, liquids have an RI, our gemstones have an RI, and it ranges between 1.4 and 2.9. And the machine that, the instrument that tells us what the RI is on the table. Next. In that light ray, which is inside now the gemstone that has been refracted, its wavelengths are being absorbed by the chemistry of the gemstone. But if you have any reds left, reds are going to bend different than the blues. So the wavelength of the rays inside the gemstone will refract differently. Only a tiny bit. I mean, it's not a big number. But the fact that they bend differently, the reds and the blues and everything in between, is important if you look at a prism. Here we have a prism. A light ray impacts it. There's a refraction. And because the reds bend less, they start to separate from the blues. Then when they hit the other side of the prism, there is a further refraction because it's going from a high dense to into air. So this spreading of this ray is what prisms do. And that spreading is called dispersion. Remember, I've introduced refraction. Well, it refracts, but the spreading of that light ray into its colors is called dispersion. Fire, you see all these colors coming out, if your eyes will allow you to do that. A diamond has a dispersion coefficient of 0.04. You don't care about that. You know that diamonds will disperse. That's a big selling point with diamonds because of their Ri. The higher the refractive index, the more dispersion you're going to get. A cubic zirconia, I got one on the table. It blows you away. It's got a higher dispersion coefficient. When you get into colored stones, the body color of the stone will usually mask any dispersion. I have some examples of a couple of transparent, semi-transparent colored stones where you can see the dispersion, but it's rare. Next. All right, back to our favorite physics chart. Our single lens, you recognize this, our single ray hits and it's refracted. In the crystalline world, and gems are primarily crystalline, some aren't, but most of them are crystals. There are 7 crystal systems. We're not going to talk about what they are, except for one. One of those crystal systems is called cubic. And those gemstones that have a cubic crystalline structure will refract one ray. One goes in and one comes down. They're called singly refractive gems, SRs, singly refractive. But the other 6 crystalline structures is what the rest of the gemstones have. And they don't behave simple like this. You have one ray coming in and you have 2 rays formed, doubly refractive. So most of the gemstones are DRs. Not only do you get 2 to worry about because they travel at different speeds, different colors, but they are polarized differently. What does that mean? Remember, polarization. So we have one of the rays are traveling through space oriented like this. If you eliminate all of these and just allow one wave in this plane, can't take the other ones, that's polarized light. Well, the other wave is traveling, it's also polarized, but guess what? It's polarized in this direction, 90 degrees to this one. So those 2 rays are complicated. But this is what gemologists have to worry about, is how to deal with them. So we have DRs and we have SRs. Next. This is a simple-minded picture of one of the 6 crystalline forms. We don't care what it is, just one of the 6. So we have a light ray coming in this side and splits into 2, polarized differently. We have a light ray coming in this part of this direction of the crystal, and it splits into 2. We have a light ray coming down the top. Guess what? It doesn't polarize. It doesn't split. This is an SR direction. So these DR gemstones can have an optic axis where there's no polarization. And when we look at these, when gemologists look at these DR stones, we see colors coming out here. We see colors coming out here, more than one. And we see one color coming out being refracted from that one. Complicated materials, or DRs. Some gems display phenomena. And I have a card up here that shows you what phenomena means. Phenomena are these crazy color patterns you get with some gemstones when they're exposed to light. Adolescence, chatoyancy, labradorescence, and so forth. Adolescence is the billowing you see in moonstones. It's a wave-like. When you put it under light and move it around, you'll see a wave-like, a billowing. Chatoyancy is a cat's eye, tiger's eye. You'll see when you rotate it under light, you'll see a cat's eye. Play of colors is opals, and so forth. So I have examples of what that is. If a gemologist can see phenomena, that limits what kind of a gemstone that could be. The last, I know you're happy to hear this, the last property we're going to talk about is the critical angle. So why is this important? Next, we see a cut gemstone. Here is a cut gemstone. It has a crown, we faceted it. We have a crown, we have a table, we have a pavilion, and when light enters the crown, which it always does, this is the way gems are mounted. When light ray hits that crown, anywhere on it, it will be refracted. Here's a ray and it's refracted. And we know the angles, so we can track it. So it goes down in this direction. It hits this faceted surface. That's the pavilion. We're internal now to this gemstone. We were reflected off at the same angle. It hits this faceted surface. It's reflected off at the same angle. And the way we have cut this, we can track all these rays. The computer tells us where all these rays are going. So we can take that ray and force it right out to the table. Well, it doesn't bounce off the table and stay inside because it's inside the critical angle. Critical angle is measured from the normal to that surface. Critical angle is unique with each gemstone. So that ray goes out. Where does it go? Into our eyeballs. And that's what we want. We want as much color coming out of this, if we're selling gemstones, as possible. So that's the importance of critical angle. If this gemstone is cut wrong, and instead of having a pavilion at this angle, next, you have a much shallower pavilion, light rays entering this gemstone, refracted, and they'll pass right out because they're inside this critical angle. So you want this to be much steeper in order to capture these rays. Stones that exhibit this poor cutting, you can see right through them. This is a poor cut. I can see my hand right through this gemstone. That's called windowing, and that's bad. So when we get to color grading, you don't want windowing. You're going to take a big penalty. The world of gems is made up of naturals. That's the stuff coming out of the ground. It's made out of naturals. It's made up of naturals that are treated in these crazy ways or enhanced in some way to improve its desirability, make it look better than what it was before it was treated. Then we have this class called the imitations or simulants. These are the lookalikes, totally different chemistry, but it looks the same. And then we have synthetics, same chemistry, same color, same properties, and drives us nuts because it is so difficult to separate synthetics from naturals. I can do it, but there's times I can't do it. So a gemologist must know about all these treatments because he's going to get one of them someday. More than someday, you might get a couple of them a day. The treatments are designed to improve the color, to improve the clarity and the durability. And these are examples of the treatments. They include dyes and heating and all kinds of irradiation. Again, next, this is what a gemologist has to understand. Today, here's the bottom line for all of you that might be interested in colored stones. All rubies are heated. I say most because if you have a ruby and your gemologist can tell you it's not heated, you have an enormous chunk of money. They are so rare. So all rubies essentially are heated. blue topaz. It's been irradiated to enhance its blue. Emeralds are oiled. Emeralds are kind of junky gemstones. They have a lot of inclusions that naturally, a lot of inclusions, a lot of fractures. Those fractures that cut through the surface, you pour oil on them, special oils that sink into the fracture and disguise its presence. So most emeralds are oil. I bought an emerald for my wife in Mexico a jillion years ago, and it was sold as an oil. I knew it was oil, but it was beautiful. Tanzanites. Tanzanites, I would say 99% of all tanzanites have been heated to improve its color. Jades are dyed. They're etched. They're filled with polymers to make it look better. Turquoise. Turquoise are dyed a lot of times. Black onyx is dyed, and so forth. So the world is full of treated gemstones. Next. Simulants, cubic zirconia, CZ, and white sapphire, and moissanite look like diamonds. They don't have the dispersion necessarily. Diamonds an SR, sapphire is a DR. So there's ways that gemologists can differentiate the two. Moissanite's a new one, we won't talk about that. Serpentine. How many times do I get a chunk of jade looking stuff from people that stop by and say, Bill, what is this? Is this jade? Yeah. I want you to say it's jade because it looks like jade. It's serpentine. Over 90% of the jades I looked at turned out to be serpentine. Again, with dyed howlite, fake turquoise. Glass. You can color glass anything. You can put certain elements in making the glass to make it heavy, like a ruby. So you can mimic the densities. You can mimic the color. What we gemologists look at. And it'll have a wide range of RIs. By the way, there's not one RI with glass in general. We look for bubbles. Mother Nature never gives us tiny round bubbles. I've never seen one. And I got a book on inclusions, and there's no round bubbles. You can get elongated bubbles. You can get bubbles in other shapes, but not round ones. So when I see round bubbles, red flags go up. Could be glass. Next. Synthetics. Again, the technological world is they just love to synthesize everything, especially those that want to make a lot of money. Synthesizing diamonds, for example, today, I brought that up there earlier, but you can synthesize all of these. People come to me with about a 1 carat red stone passed generations through their family. Is it a ruby? Well, there's a quick test for a ruby, and that is whether or not it fluoresces under UV. So I take my UV flashlight, put it on there, glows like crazy. I say, oh, the good news is you got a ruby. The bad news is it's probably synthetic because they've been making rubies since 1910. The world is awash in them. Synthetic diamonds are now mainstream. They used to make them only in a half a carat. They're making 5 and 10 carat synthetic diamonds today, and the price is almost 1/10 the price of a natural. Detection of synthetics requires expensive equipment. I don't have it, but we are given guidance by the research community as to what to look for with light to help identify synthetic diamonds. Next. This is why you came here. You're now going to learn about the process. So don't leave now, because this is what you came here for. So this proven process, we will go through a bunch of steps in identifying a gemstone. We're going to start off with general observations. And even though you can't read all these where you're sitting, we're going to follow in this order. So the basic instruments that a gemologist must have, basic, are listed here. A loupe, a 10 powered, a lamp, a light lamp, sitting right there. I have a daylight equivalent fluorescent. A microscope. My microscope is 10 powered and 30 powered. And there's a special well at the bottom of my microscope that's lit specially so that it enhances the inclusions. I can see the inclusions much easier when it's in that well. That's called dark field. So my microscope is dark field, 10 and 30 power. Refractometer, polariscope, spectroscope, microscope, a UV lamp, which I have on the end of the table, a magnet, and an instrument to measure specific gravity. These are all on the table, and we'll talk about them. Loose stones compared to mounted stones in a setting, it's light and day. I hate being given mounted stones because it takes out a lot of the testing that I can perform. The prongs get in the way. You can't see through it easily. So this talk today is not how I deal with mounted stones, but how we deal with loose gemstones. General observations, that's the first one up here. The stone that I have selected to evaluate is a blue stone, which I have in my microscope. We don't know what it is. It's a gorgeous cobalt blue. It could be a very expensive sapphire, blue sapphire. It could be a very expensive blue spinel. It could be a very expensive zircon, or it could be glass, okay? We don't know. We're going to put it through the test. So we record. This is the information we're beginning to collect. Just observations. Its color, blue. Is the color uniform? Yes. There's no layers, different color zones. Is it transparent? Yes, it is. Is it cut? Yes. It's a cut stone, rectangular in shape. What's its phenomena? We'll get to that in a minute. What's its luster? I'm not going to talk much about luster because it takes time. But luster is essentially the crispness of the light that's reflected off of the gemstone. If you have a polished piece of hematite, which I have here, you have a super crisp reflection. If you have a jade or an amber or something that is not hard and highly polished, you'll get a different luster. So luster is not a critical one, but it's important for the gemologist to record. Dispersion. I take this blue stone, I put it up to light, move it all the way around. I see no dispersion. I note that. Heft. Heft is the weight. This is a qualitative thing, but if I had a piece of hematite, I could say that's heavy. This particular blue stone, it's moderate. It's not a big deal. So I record it as the heft is moderate. Is it magnetic? I take my magnet, which is pretty strong, put it up. There's no magnetism whatsoever. I make note of that. It's an assembled stone. Assembled stone is a stone that has more than one layer. This is Spencer opal, a Spencer opal triplet. It has 3 layers. There are other stones that you can, that people talk about that are made up of other layered stones to fake out a gemologist. We won't go into that. But in this particular stone, it's just one chunk of stuff. So it's not assembled. Phenomena. Stars. None. Chatoyancy. Rock back and forth. None. Color change. I have that color change. This is, I put it under daylight, certain color. If I put it in under incandescent, is it change colors? There are color change gemstones. No, not this one. It's blue, blue, blue. Is there any iridescence, labradorescence, or any play of color, address? None, 0. So no play of color. And I have examples of all those plays of color up here, so you'll know what to look for. Now we go to the microscope. Very important. We look for inclusions, fractures, gas bubbles, needles, platelets, and so forth. Curved striations. Synthetic materials or natural materials, when they form, the growth lines, when they're forming jillions of years ago, are normally parallel. The growth, they grow in that direction. Synthetics, they curve. If we can see growth lines, they're hard to find, that are curved, that's a red flag. That indicates we probably have a synthetic. So we look at this and there are pictures of inclusions of all these kind in books. And I got a book here full of pictures of inclusion. So if I have an inclusion that I don't recognize, I'll go to that book and that will tell me, you got this kind of stone, this is the kind of inclusion you're going to get. So then we look at the fracture surface. This particular gem has not been fractured intentionally, but the facet junctions, remember this is a faceted stone, the facet junctions are chipped. And there is a large chip on the edge of this blue stone. And it's a conchoidal fracture. That's important because there are certain gemstones that fracture in a conchoidal manner. And I have a conchoidal specimen on the table. Is there any dye? I say no dyed lines at all. No indication of being dyed. Is there any coating on there? I look at the facet junctions. I don't see any chipping or coating. All I see with my blue stone are tiny bubbles. These bubbles have been cut when the stone was fractured. So you see little indentations where that round bubble used to be. You only see in a half of a bubble. And inside that stone, I could see under 30 power, not 10, in dark field, I can see some small bubbles. Next. We're going to get the RI right now. The refractometer can take opaque or transparent. It requires a smooth, flat surface. So if somebody gives me a gemstone that's curved or rough, I have to make a smooth, flat surface. I can deal with a curved, smooth, or polished, but it drives me nuts. It's very hard to get an RI with a refractometer with a curved surface. It can be done, but it's tough. If you have a rough surface or a surface is not polished, forget it. So we're going to take our gemstone next, and we're going to put it into our refractometer. Remember, we don't know if it's a DR or an SR. If we put this stone, here's the D, we've seen this before, this is the DR stone, and we look at the refractometer, which will give us a number straight away. This is its refractive index. Refractometers are super complex. They have a ton of physics built into them that would take me a day to go through it. If I turn that stone in the refractometer 20 degrees, I could get another RI. Turn it again, I could get another RI. No big differences, but a difference nonetheless. What does that tell me? More than one RI? That's got to be a DR. The refractometer requires a special liquid. You put the stone on this platform, but before you put it on the platform, you put this tiny, tiny, tiny drop of this special liquid. This is to make sure that the light that comes into that refractometer is not upset by air bubbles. If you want a continuing material between that light into the stone and out of the stone. That special material is toxic. The RI is dependent on the RI of that special liquid. Unfortunately, for normal folks like myself, this RI liquid limits RIs to 1.81. There are not a ton of gemstones that have an RI greater than 181, but there are some, diamond being one. So the refractometers have a limit, 1.81, because you're limited by that particular fluid. There are fluids that can take you higher than 181, but they are so toxic, I couldn't buy them. I mean, they're forbidden. Big labs will have those, but not gemologists. Or next. So, okay, next. Now we're going to go into a polariscope, and this will confirm if it's an SR or DR. But my polariscope can't take opaque materials because I have to get light through it. We're going to use a polariscope, and we're going to back it up with a dichroscope. What is this word pleochroism? Back to that crystal that shows two rays coming out with different colors, one side and so forth. Pleochroism is the ability of a gemstone to pass different colors, transmit different colors. That's all it means. But the number of colors and the color themselves is part of pleochroism, and that's what I have to record. Next. So I put the stone in the polariscope and I adjust the light. I'm looking through a polarized lens. I adjust the light so with my lens so it looks dark. And then I turn that gemstone. And if no matter where I turn that gemstone in that polariscope, it stays dark, it's an SR, because there's only one ray coming out. No matter where I look, it's the same ray, and I've cut off the light, it stays dark. With DRs, there'll be another ray coming out, and all of a sudden I'll turn this thing and boom, light's going through it. So it's called blinking. So if my polariscope blinks, when I turn that stone in it, it's a DR. The dichroscope is important. With a DR, here I'll illuminate the gemstone with light behind it, and I'll put this polariscope up there, this dichroscope, and it will tell me the colors. It will tell me, looking at this particular, remember, if you look at it all kinds of directions, I can see two colors coming out here. If I look at it a different orientation, I can see another color. This is blue and gray, this is blue and red. And then if I'm looking down the optic axis, I'll see one color. So number of colors and what the colors are is important in Gem ID. We already know it's a DR. In my blue stone, blue, 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 all the way around. It's definitely an SR. When I look at it through a dichroscope, it's one color, no matter how I look at it. Specific gravity. That's the instrument on the end of the table. It's defined as the weight of the material over the weight of an equal volume of water, which means that it is the weight of the material in air over the weight in air minus the weight in water. So you weigh it in air, and then you weigh it in water, and there's a scale on this instrument, specific gravity instrument, that tells me exactly what the specific gravity is for what I am weighing in air and water. Specific gravity is very important property of a gemstone. Next. The gemstone spectrum. I measure that with a spectroscope. And this tells me what light waves are transmitted through the gemstone when I put light behind it, and what waves are absorbed. It's an important property of the gemstone. So I take the gemstone, I take a light, and I've set up down here to show you that. And I take my spectroscope and I put it up against the gemstone, and it tells me I see reds, yellows, greens, blues. I see the whole spectrum of light waves coming through. But I also see black lines, and those lines are the absorption lines. Those are the wavelengths that don't get through. And the spectroscope shows them as black lines. And this is a kind of a poor copy. It shows this is for a garnet. And I look through the spectroscope and I see reds, I see yellows, I see greens, and I see everything down to purple and blues. And I also see these black lines. And at those wavelengths, by the way, my spectroscope does not have a wavelength scale. Some do, more expensive. But I can guess where these wavelengths are because I know it's between yellow and green. So this is a signature of gemstones, and there's a whole book about what these spectrums are for various gemstones. Is them another test? Is it fluorescent? If it is, I record the colors. I go to my box down there at the end of the table, which is a UV source. This particular UV source, next. This particular UV source, I can flick a switch and it irradiates my gemstone in the UV length of 366. Remember, it's just less than 400. There's also a shortwave UV, which is 254. So I can toggle between long wavelength and short wavelength. And guess what? My blue stone has a very strong chalky blue fluorescent at shortwave. It has a chalky blue at long wavelength, but it's much less intense. So I record that. We don't have a diamond, but I just wanted to point out that there is a device that helps the gemologist. It's called the diamond tester. And instead of going through to identify diamonds using all this equipment, this device sends a pulse of thermal energy because diamonds have a high thermal conductivity. So I take my wife's ring and I put my, first of all, I have to warm it up, which I don't have time to do, but I put this tip, which will send a thermal pulse on her diamond, boom, says you got a diamond. It's that simple. The good news is it's probably a diamond. The bad news is there's one more gemstone that has a high thermal conductivity. It's called moissanite. But there are ways that I can separate moissanite from diamond. Moissanite's a DR, diamond's an SR. That's one way. But this is a diamond tester that's really good for quick analysis. A destructive test. We're almost done. A destructive test. HCl, muriatic acid, you can buy it at Home Depot. You put a tiny bit of muriatic acid on the stone, and if it fizzes, it's a carbonate. And guess who lives in the carbonate world? Malachites, rhodochrosite, calcites, marbles. So this gives us right away a narrowing of possibilities. In this case, I put a drop on this stone. It's not going to affect its appearance because it's a real tiny, no fizz. Next. Last, the hardness. All gemstones have a hardness measured on the Mohs scale. What is the Mohs scale? It ranges from 1 to 10. 1 is like soap, it's that soft. 10 is diamond, the hardest thing we know. So I have a set of hardness picks. There's 4 of them. And on each end of the pick, there's a tip, and that tip has a certain hardness, a Moh of 6. That one has a Moh of 7. So I'll take, this is destructive. I'll take my gemstone, it's not faceted, but it's a chunk of rough, and I'll see if I can scratch it with a Moh 6. If I can scratch it with a Moh 6, that means that that gemstone is softer than a Moh 6, probably a 5 or 4 or 3, and we can use these to tell us real close what the hardness of that gemstone is. And the hardnesses are recorded in books, and that's a big help, especially in the field. When I'm out in the boonies, I want to know what this particular material is. Is it an agate? Is it a whatever? And I know the hardness of agates, and I can use my picks to tell me right away. In Arizona, quick, time-consuming story. A super valuable material is called gem silica. It is chrysocolla that is mixed with agate. Super expensive. There's also chrysocolla by itself. So in the field, if I find something looking the color of chrysocolla, which is a bluish thing, I will use the hardness test right away to tell me if it's pure chrysocolla, a gem silica, which is an agate, has a hardness of about 6 or 7, or is it chrysocolla, where it has a much softer one. So anyway, next. So we have collected all this information on our blue stone. Now you're almost ready to go home, except after we make a call, there's grading and valuing. So don't leave quite yet. But we're at the end of conducting our tests. We have collected information from general observations on our blue stone. We've looked at our magnifications, and guess what? I found a few tiny bubbles. The facet junctions were chipped, meaning that the hardness is not great. There was a large conchoidal fracture at one of the facet edges. No dye, no coatings, whatever. Measured the refractive index, 1.62. Next. Optical properties. We know it's an SR. We measure the specific gravity, 3.7. We know its fluorescence. We know its visible spectrum. I could not see, and I've looked hard at this blue stone, I could not see any absorption lines. However, when I looked in the red and orange areas, that were being transmitted, they were dark, no black lines, but it was subdued, it was dark. Like there is some absorption going on in the reds and the orange. I put a drop of acid, no reaction. Its hardness I can't do because it'll scratch it up. So I compare all this information to all the information that's ever been generated on gemstones. You say, well, how can you do that? Well, you can do it because GIA has given me 2 sheets of paper, one with 67 common gemstones and another one with 63 not so common gemstones. So I have 127 gemstones. All the information has been taken from books, voluminous amounts of information, and put on this chart. So as I read across the top, what does it say? This is the gemstone name. This is all the colors you can find it in. This is it transparent or opaque? What's the phenomena? What's the RI? Is it an SR or a DR? What's its pleochlorism? How many colors and what are they? Spectra. What do you see? Do you see any of these absorption lines? What's its fluorescence? What's its specific gravity? What's its hardness? What does its fracture look like? And some comments. It's all here. So I take all this information and I take this and I see if there's a match. For this stone, bingo. Now, I'm usually not that lucky, but we don't have enough time to go into the difficult ones. Guess what it is? It is a cobalt colored blue glass. So we have finished with our gem ID and we're going on now to grading and valuing. Diamond grading was pioneered by GIA in the 1950s. It's been used for a long time. Everybody uses it. It's commonplace, and nobody has criticized the grading criteria. So the first thing that GIA does is decide on a color grade. Color in diamonds is a no-no, except fancy ones where you get that. So you don't want color in diamonds. So the color grade goes D through Z, D being colorless, Z being increases in tints of yellow, or as you get towards Z, you might get some brown. That's bad stuff. So, but you come up with, because you have guides, master sets, you come up with a color grade. Let's call it a J. It has a little bit of yellow. What's its clarity? This is all using a 10 loop. You don't need a microscope. I do because my eyes aren't good. But GIA going through their grading school, 10 power loop, that's all you need. Clarity, inclusions. IF, nothing. You never, hardly ever see an IF diamond. It's got something in it. So there's 10 grades, VVS 1 and 2, VS 1 and 2. VVS 1, you're looking, here's the guidance. And I've gone through this. I mean, it drives me nuts if your eyes aren't good. Minute, you're looking for minute inclusions. That's VVS 1s and 2s. VS 1s, you're looking at minor. How would you like to handle that one? It's not minute, it's minor. You got to do a lot of looking at stones to figure out the difference between that. Then you get into the SI 1s and 2s. Noticeable. Oh, really? What's the difference between noticeable and minor? You have to know that. Then you get into the eyes, which I call fish gravel. There's so much junk in there. You can see it with a naked eye. They're not attractive, but guess what? They're cheap. So you buy a diamond with an SI2 or getting the eyes, you can afford it. As long as somebody doesn't spend a lot of time looking at it. So color grading depends, clarity grading depends on the type of inclusion, the size of the inclusion, the location. If that inclusion is under the table, you're going to drop down a notch or two because you can see it. If that inclusion is stuck at the edge of the facet, a lot better. And the number of inclusions. And then we weigh it, the carat weight. The carat weight's important with diamonds because with larger stones, it's worth more per carat. Then we look at the cut grade, and there's been some changes in this in the last 3 or 4 or 5 years. But the cut grade is excellent, very good, good, fair, poor. How about that for subjective stuff? But you look at the brightness, the fire, the scintillation, which is the light rocking back and forth when you put it under a light. You look at its polish, the symmetry of the cut. Cutting diamonds is should be a precise skill. You have angles that must be matched. You have for various faceted diamonds. And if you stray from those proportions, then you take a cut, you take a hit in the cut grade. So what are we stuck with? We're stuck with color, clarity, carat, and cut. And we have the grade for the diamond. You go into any commercial price list for diamonds. And for that color, for that clarity grade, for that carat weight, for that particular cut grade, it tells you the wholesale price of that diamond, the wholesale price at the retail. Bang, right away. So it's nice relative to colored stones, which you'll hear about. Some people that use GIA's diamond grading, and most of them do, they like to take further deductions from the wholesale price due to its fluorescence. Believe it or not, diamonds that fluoresce, and there's 30% of them that do, that's not good. Clarity enhancements. Has somebody drilled a hole to take out an inclusion? And when you get into the browns, the colors N through Z, some people take additional penalty. And then for certain types of cuts, it's worth more than other cuts. So there are other considerations depending on who's doing the grading. Next. The grading of colored stones is a nightmare. The bottom line, there is no generally accepted grading criteria for colored stones. Now, how can that be? GIA again stepped into the breach in the 1970s and said, this is crazy. People are just choosing their own grading and people don't understand it. You can't compare it and whatever. So GIA stepped into the breach and they created a colored stone, faceted color stone grading. And they started out by selecting its color. The color is from the color wheel, 31 hues. You select a tone and saturation. Oh, I hate that because that's subjective. And then knowing that hue, tone, and saturation, you go into what GIA provided years ago, a color chart. Remember, you've gone through the ID process. You know it's a beryl. You know it's blue-green. You pick that off of the color wheel. So you go into the chart for a beryl, blue-green, and you have these boxes. Here is tone from 2 to 8. Here is saturation, 1 to 6. And if your green stone is a 4 saturation and a 5 tone, your score is 6.4. If you happen to have more saturation, you could hit bingo. That's the highest grade you can get, a 10. If your tone and saturation puts you outside this box, you can't call it an emerald. Only those that fall inside this box, you can call an emerald. You have to call it a green beryl. And of course, you know what that means to the price. Boom. Next. So we've graded, we've gone to the color grade, GIA's technique, and now we're back to grading cut and clarity. So GIA has, no, back. So we've graded color. We're going to grade the cut. We look at its facet proportions, just like diamonds in a way, because GIA is using their same 4C that they use, mentality that they use on diamonds. The facet proportion, the symmetry, the polish, and there the grade is excellent, fine, good, whatever. subjective. They grade clarity, but with colored stones, there's another element in clarity. It's what type is that gemstone. Type 1 gemstones are eye clean. That doesn't look like they have anything in the way of inclusions. Type 2s, they have a moderate level of inclusions. Type 3, they're loaded. Okay, so how do you grade a type 3, which is emerald? How do you grade an emerald when it's loaded? What color grade or what clarity grade do you give it? Well, if it's loaded times 2, you take a deduction. If it's just loaded, you don't take a deduction. And if it's loaded lightly, you enhance its grade. So you have to know, and they're listed, what gemstones are types 1, 2, and 3. So when you have this information and you've done your homework, you end up again with a subjective grade. The carat weight is important, but it doesn't affect the grade. It does affect the value, but not the grade. So you end up, GIA, remember they stepped into the breach and they came up with something. You end up with an overall grade, which is the combination of all these, and it's excellent, good, bad, whatever. And the story doesn't stop there, because dealers and sellers of colored stones look at things a little bit different than if you were a GIA grader. And so, because it's rather subjective in these areas, there were some relatively wide differences between people doing the gem grading. GIA results were useful because, remember, there was nothing before they stepped in, but it was highly subjective. What that caused dealers to do is to divert away from GIAs and start to make their own, because they weren't happy with the differences. I will grade my own. And they came up with their own techniques, still basically the same, but they don't use excellent, high, grade, better, or whatever it is. They've come up with AAA grades, AA grades, A through B. The bottom line is the colored gem faceted world could not come up with a better technique than GIA. A lot of people didn't like GIA. So the situation today is there is no universally acceptable method to grade a colored stone. Last couple of years, however, 2 companies have stepped into the breach. One in particular I like. It's developed by Gemworld, which we'll talk about in a second. But guess what? Who does not grade colored stones? GIA. Why would they? They know the problems in using their technique. They teach us how to grade colored stones using their technique, but they don't. You can't send a colored stone to GIA and have it graded. You can have it identified. GIA will do that happily. So can I. But they don't grade colored stones. A few other companies will. And I looked at them on the internet, and they're kind of spooky. But nonetheless, there are those that will grade colored stone. Next. What's the situation today? I said there's 2 new kids on the block. They've improved upon GIA's technique. Gemworld is the company. They've increased the hues to 100. They've increased the saturation levels to 16. But more important, this is the big one. They provide pictures for all combinations, for all their 100 hues, combinations of hue, saturation, and tone. I can go with my stone and turn a few pages, and I can find that hue, tone, and saturation, bang, just like that. I don't have to guess. Now, it's taken a lot of money and a lot of time in order to get the printing right, which is a challenge. But nonetheless, I have their book, and I find it just so refreshing not to have to fight the hue, tone, and saturation problem. In addition, when it comes to clarity, they have made more detailed criteria built into their clarity. So it's not at all as subjective as GIAs, and the same for cut. So you start out with a color grade. This is GemWorld's, which is very similar to, you identify the color, the hue tone, saturation. You go into colored charts. You pick off the color grade like 8.7, and that's what you start with. And then you deduct numbers from that 8.7 due to its clarity and its cut. And you end up with a final grade 1 to 10. If you started out with a 6.5 and all the deductions brought you down to 4.7, well, that's the final grade. It'll be from 1 to 10. And then you go into Gem Guide's bi-monthly price list for diamonds and colored stones. And for that colored stone, for that carat weight, for that score, you get a wholesale price number. So it is slick. Is it subjective? It sure is, because that color chart reflects what's called the desirability of people wanting that color. How do you get that? This company goes and talks to everybody. They've been doing it for years. They talk to all the jewelers, all the dealers. So that color, when you see a 10, for example, that means that's the most desired color for that particular gem. And is it subjective? Yeah, it is. Will it change with time? Yeah, it will. But right now, they've been out for 2 years. It is not widely accepted. People haven't thrown any rocks at it, but it just hasn't been out there long enough for people to use it and get used to it. Costs a lot of money to buy that book, but it really helps a gemologist. Now, there's also an issue I haven't talked about in Gem Guides, they also bring in treatments, deductions for certain treatments. Country of origin is a big one now. This grows like crazy. They're able to identify some gemstones where they came from. If you have a Colombian emerald, it's worth more than an emerald from Zambia. So country of origin is factored into these, Gem Guide is factored into their wholesale price. Next. We're nearly done. So the factors that include the final grade are, who's doing the grading? Well, it's a big business. I mean, it's a big business. And there's a lot of companies now in the business of grading, in this case, diamonds, grading. I said the grading of color stones is a mess still, no widely accepted. So I'm gonna, this final grade I have written up here just for diamonds. There's lots of labs doing the grading for diamonds. And GIA is probably the most respected along with AGS. If you do your homework and you look online as to what people are saying about these other labs, you will be surprised. I walked into a jeweler about a month ago, and I saw all their diamonds being graded by one company. I've never heard of them. And I asked, I said, how long have you been? This is not a mom and pop jewelry store. Well, our company contracted with this company to do our grading. Well, that company could, I'm not saying they did, could grade it higher, because we know there's evidence some of these grading companies grade higher. What does that do? It puts money in the jeweler's pocket because he can get more for that higher grade. And if that company competed with others to get that jeweler's business, he's probably doing okay, selling his grading skills and helping the company's bottom line. So there could be a symbiotic relationship between the jeweler who is buying these services and the company provided. I don't want to scare you up because this doesn't happen a lot. But if you are buying and selling a diamond, and you have any concern about who's doing the grading, go to an independent gemologist and say, give me a check on what this grade is. Not that a gemologist has all the equipment necessary, but he can give you a check. Okay. Last one. I said in the advertisement of this class, what's it worth? What is it and what it's worth? Well, you know what is it, how we did it. What's it worth? I used wholesale price for the cut stone as the metric for value. It is not what you could take that stone and sell it to somebody for. It's not an internet price. It's not an auction price. And it's not what you would buy that stone from a retailer. It's the wholesale price. But what it represents is an understanding of what it could bring. I have sold diamonds. I have sold a few other stones, and I use Gem Guide to get me into the right area of the particular universe. When you sell or buy diamonds, you will never find a diamond these days that's not certified. Didn't used to be that way, but now the public requires formal certification of all diamonds, not from Bill Thielbahr, but from one of these diamond labs that exists out there. GIA being, as I say, one of the best. And I'm not selling GIA, I'm just saying that's a statement of fact. GIA might be more expensive, but I'll leave it at that. Okay, guys, you hung in there. You're probably saturated, but that just comes with the turf. So I'm here to answer all questions you've got if you're still awake. And you're free to come up and look at all the goodies on the table, and I'll answer any questions about the equipment.